After we have learned about the most important parts of the random forest algorithm, we can now apply it upon the iris dataset. And let me anticipate that the preparation of the data will be more work than the actual random forest model, which is the reason why I want to discuss a few things in advance. The division into X and Y data is a central component of data preprocessing. But what is our X data and what our Y data? Our X data are the features that we provide as an input into the model. This is the data from which the random forest should make a prediction about the iris species. In this example, this will be the sepal length, sepal width, petal length, and petal width. Our Y data will be the species. We also call it the target data, which we provide so the model learns how to build up the decision trees that the classification is done correctly. We only need the Y data during training and validation, as later the model should do its predictions only based on the X data. Even though the model would not crash if we put in the Y data as it is, it makes a lot of sense to turn those species names into numerical classes to avoid problems. In general, AI algorithms work with numbers and not strings, so we should turn everything into numbers when training and using them. So we will turn those strings into numerical classes, one value for each possible species. Then we are going to use those numerical classes as our Y data. Now we have our X and Y data, but at the end of the last lecture we talked about model validation, and that we should keep a part of the data for testing the model's performance after training. And we do that by randomly picking samples from the data for training and testing. We will call the X data that we pick for training X-train, and the corresponding Y data Y-train. Then we also have observations which we have not picked for training, which the model has never seen. That will be our X-test and Y-test data. Randomly picking observations from the dataset while keeping track of corresponding X and Y data seems to be quite a bit of work. And that's why we will keep it simple and use the train-test-split function from sklearn for that. So let us go to our programming environment and start with our first machine learning model. For data preprocessing, we will only need the pandas library and take care of the other libraries later when we need them. So import pandas as PD. Next, we can already load the iris dataset, which lies as a CSV file in a subfolder called data. I will use the variable name df, which should stand for data frame and is commonly used. Then I call pd.readCSV and provide the relative file path of our dataset, meaning the path I have to take from where this script is currently stored. To tell Python that this is a relative path, I say /. Then I provide the subfolder data, and within this folder we can find the file iris.csv. Then I print the head of the data frame with df.head. As you can see, this data frame only seems to hold data for the species Iris setosa. This is just due to the fact that the data is currently sorted by the species name, and the command .head only provides the first 5 rows by default. So let us check if the other species are also in the dataset. I get our data frame, then select only the species column within square brackets, and say .valueCounts, which is a method that we can call upon a data frame or a data series. So this is nothing that I just invented, but it is a fixed expression that comes with the pandas library. Now we can see that there are not just observations for Iris setosa, but also for Iris versicolor and Iris virginica. And each species has got 50 observations. Next, we should do something that you should always check for if you haven't created the data by your own. Looking for no data values in your dataset, which we usually refer to as none or NaN values, standing for not a number. We will only do a quick check with df, then call the isNull method to check for none values in each position of our dataset. and then call dot sum on that to get the total count of none values for each column. You see that we don't have any none values in our dataset. However, this method alone would not be sufficient if you start with your own data. It can happen that the person who generated the dataset did not code the no data values with none, but with a different value, like -999. In this case, we would not have captured the no data values. So always look into your dataset and see if there are specific no data values. In case we would have caught some none values with this approach, we could remove those observations with df.dropNA. Now let us take care of our Y data. Currently, the Y data is represented by the species names. To easily turn them into numerical classes, we will use the label encoder, which is provided by scikit-learn or sklearn, how the library is called when we import it. But first we have to import the label encoder in order to use it. So we say from sklearn dot preprocessing import label encoder. Then we create an instance of this label encoder class behind the variable LE. As we want to store the numerical classes in a new column, I set up a new one by getting our data frame and provide column name which is not present yet. I will call it class. Now I want the numerical classes to be written into that column. So I get our label encoder LE and say fit transform. And then I provide the column where to find the species names, which is the column species within our data frame. The way we set up the label encoder and use it on our data is again something that is given by the library and nothing that we decide. Looking into the documentation of scikit-learn helps to understand how to apply the methods and functions. Let us see how the data frame looks like. We have the species names as well as a numerical representation of the class. As we don't really need the species names anymore, we can also remove them with df.drop. Then we provide the column name, the axis along which to find it, which is axis 1, and make it an in-place operation, so it is removed from the current data frame. If we print the data frame again, we only have the numerical representations of the species. Now we are ready to separate the data into X and Y data. I will do this with the ilog method to extract the columns by their index. First, the X data. We say df.ilog and provide the indices within square brackets. The first position belongs to the rows, and as I want to select all of them, I set a colon. The second position is for the columns, and here I want to select the columns with the indices 0, 1, 2, and 3, which store the sepal length, sepal width, petal length, and petal width. To choose those first 4 columns, I say colon 4. This operation is non-inclusive, so it means select all columns up to, but not including index 4. Now we need to grab the Y data, which we also do with the ilog. And all columns, but with the specific index 4. Behind the index 4, we can find the column with the classes. Let us check if we have done no mistakes by printing the head of the X data. This seems to be alright, and now the Y data, which only seems to include the numbers of the classes. So our X and Y data is prepared, but we want to spare some data for testing the model's performance. And that's where the train test split comes in. As the train test split might seem to be complicated, I want to look into the documentation. You will find some examples on how to use this function a little bit further down. You see that train test split does not return a single value, but a NumPy array or pandas data frame for each of xtrain, xtest, ytrain, and ytest. This means that we can directly provide those four variables to store the respective arrays in the correct variables. The order of xtrain, xtest, ytrain, and ytest is fixed. So I will copy this part from the documentation to make sure I do not mix up anything. The train test split function also needs some additional information from us. First, what is our x data? Our x data is stored in the variable x. For our random forest model, we could just provide the x and y data as a data frame. But in the later lectures, we need them to be NumPy arrays. So let us get used to NumPy arrays from the beginning and turn this x data frame into a NumPy array. You can do that by calling .values on our x. Next, we provide the y data, which we also turn into a NumPy array. Then we can define how much data is going to be selected for testing. I will set the test size to 33%. The next argument will be the random state. This is an argument that you do not necessarily need, but it will ensure that your data is sorted into training and testing the same way as it happens on my machine, at least if you provide the same number as I do. I will use the value 42 for that. In case you are wondering why a lot of people choose this value, it is a reference to the Hitchhiker's Guide to the Galaxy and is supposed to be the answer to everything. The last thing that we need to do is to set the shuffle to true. This makes sure that the data is randomly shuffled before it is sorted into train and test data. And this is crucial in our case, as the data frame was perfectly sorted by the species names. Let us now check the shapes of the resulting arrays for training and testing. I will do this with a short fprint statement to get the array's shape for each of those variables. Xtrain and ytrain hold the same number of observations. Xtrain holds the 4 input features per observation, while ytrain only holds the single numerical classes, as indicated by the comma nothing. As we want to spare a third of the data for testing, xtest and ytest hold 50 observations. Xtest again with the 4 features per observation, and ytest only with the numerical classes. At this point, our data preprocessing is done, and we can set up our random forest model. But we will add 2 more imports first. As we will use the random forest classifier that is provided by the scikit-learn library, we import it from there with from sklearn.ensemble import random forest classifier. And from sklearn import setconfig, which we will only use to print the configuration of the random forest model. By default, the model settings will only be printed for settings that we changed from the default values. But as I want to show you how many settings we can make, we use the setconfig and set the print changed only parameter to false. Setting up and training the random forest model will take exactly 2 lines of code now. We will store the model in a variable that I call model. Then I get the random forest classifier class and set some parameters. First, the number of trees that we want in our forest. This parameter is called n_estimators. If you take a look into the documentation, the default value is set to 100 trees. As I want to save some time, I will only use 2 for now. Then the criterion. We can choose between Gini, entropy, and log loss. We haven't discussed the latter, but we know Gini and entropy. I will go with entropy for now. Then I will also define the max features and set them to 3. You might remember the bootstrapping approach from the theory lecture. During bootstrapping, not all features are considered in each tree. And this is the parameter that controls how many features should be considered. The default value is the square root, but as the square root of 4 features is only 2, I set it to 3. Now it's time to train the model. And we do that by taking our model and say .fit on that. As the model currently does not know the data it should be trained on, we need to provide xtrain first, and then the corresponding ytrain. Then we execute the cell and our model gets trained. After this is done, we want to know about the model's performance. To do that, we first need to know how to deploy the model and do predictions. The first predictions that I am going to do now will be based on the xtest data. So the data we have not yet shown the model. I will store the predicted classes in a variable yprettest. Then get the model and say .predict on that. As an input, I provide xtest. You see that the model now makes a class prediction for each observation in xtest. We had 50 observations in there, so there are corresponding 50 predictions. But looking at the predictions alone does not give any information about the model's performance. So we need to compare them to the actual classes to calculate the accuracy of our model. I will import two more functions from sklearn.metrics, which are accuracy score and confusion matrix. Let me copy the test data prediction so we have everything in one cell. Then I make a print statement for the accuracy of test data and put the calculation of the accuracy into the brackets so it is directly calculated. For that, I get the accuracy score and provide the real test classes, ytest, and the predictions we just made with the model. Now it is very common to do the same accuracy calculation for the training data as well. You might wonder why we should do that, as this is the data the model has been trained on. But having both the accuracy of the test and the trained data gives an idea about how well the model can generalize. So let me copy that and change all necessary parts for the training data. You see that in our case, the model received very good results on the training and testing data. If the accuracy under the training data would have been way higher than under testing data, we should think about whether the model might fail to generalize and would need to change some parameters. But in this case, everything is fine. I quickly want to show you that we can calculate the same metric with model.score. You see, many roads lead to Rome when programming. The accuracy gives a general overview how many correct classifications we have, but we don't know which observations have been misclassified into which class. And that's what we will use the confusion matrix for. To plot this metric, we need to import matplotlib.pyplot as plt and import seaborn as sn. Both are libraries to plot data into figures. To get the confusion matrix, we set up a variable which I will call cm. Then get the imported confusion matrix and provide ytest and yprettest. So we calculate the matrix for the test data. Then we plot the results in a color-coded confusion matrix with the help of seaborn. So sn.heatmap, provide the calculated matrix, and set the annotations to true, so we see the numbers of observations. Then I set the x label, which I want to call predicted, and the y label, which I call truth. Now let me briefly explain how to interpret this figure. 19 observations that the model classified as class 0 actually belong to class 0. And the model did not misclassify a single observation as class 0 that actually belonged to a different class. 15 observations that the model classified as class 1 actually belong to that class. But it classified one observation as class 1, which actually belongs to class 2. You see that the diagonal represents correctly classified observations, and all other positions show how an observation has been misclassified. The last thing I would like to show is the feature importance. It shows how important each feature was within the model to do the splits. First, I get the feature names of our X data from our initial X data frame. Then I set up a variable feature im that will store a pandas data frame, which shows the model.feature importances. And the index should be the feature names that we just extracted. Then I sort the data frame, so the one with the highest value is listed at the top. It is very likely that you have different values within the confusion matrix or this feature importance, as the bootstrapping has got random factors that might lead to different results. If you rerun the whole script, you will probably also receive different results, which is again due to the random factors within the model parameters. Speaking about the model parameters, you see that there are a lot more parameters that we could have set for the model. I recommend to play around with at least those parameters that we used, like setting the number of trees to 50 and using Gini instead of entropy.